Ever found yourself in an argument with a friend about which movie to watch? You want horror, they want sci-fi, but somehow you both agree on thrillers. How do you actually see that compromise? Welcome to the world of the Venn diagram. It's not just a bunch of circles on a chalkboard, it's one of the most powerful tools in the world for sorting information, making decisions, and solving complex problems. Today, I'm going to show you exactly how to master them in under 6 minutes. Let's start with the basics. A Venn diagram is a visual map of relationships. First, we have the universal set, the big box that contains everything we're talking about. Inside that, we have our sets, usually represented by circles. The magic happens in the intersection, that's the overlapping middle part. That's where items that belong to both categories live. Everything outside the circles, that's the complement, the stuff that doesn't fit into our chosen categories at all. It's simple, but it organizes chaos into clarity. Okay, let's build one together. Imagine we're comparing people who play guitar and people who play piano. Step 1. Draw your two circles. Label them, guitar and piano. Step 2. Always, and I mean always, start with the overlap. Who plays both? Put them in that center slice. Step 3. Now, fill in the unique parts. In the guitar circle, write the names of people who play guitar but not piano. Do the same for the piano circle. Step 4. If there's someone in your room who plays neither, they go in the white space inside the box but outside the circles. See? You just took a group of people and instantly visualized their skills. Now, what happens when life gets more complicated? You can add a third circle. Suddenly, you have 7 distinct regions. It looks a bit like a flower. This is used in professional fields like computer science and data analysis to find exactly where variables intersect. It's actually the foundation of set theory. Whenever you search for something on Google or filter items on an Amazon shopping page, you are literally using a digital Venn diagram to narrow down your results. 5:15. Why this matters, so, why should you care? Because we make decisions every single day. Should you take job A or job B? Which features do 2 different smartphones have in common? How do you manage your study time across different subjects? We can represent sets in Venn diagram in 5 ways. Disjoint set, subsets, intersecting set, equal set, complement of sets. Sometimes, groups of data have absolutely nothing in common. We call these disjoint sets, or mutually exclusive sets. As you can see in image, we have 2 distinct circles within our universal set, one representing students who play soccer, and the other for students who play chess. Because these 2 groups share no common members, the circles do not overlap at all. In mathematical terms, this means their intersection is empty. Now, let's look at a more specific relationship. A subset exists when all the members of one set are also contained within another, larger set. As visualized in image, we have a universal set, all students in class 10A. Inside this universe, we have 2 defined groups. First, the large blue circle, students who take maths. This group includes Mia, Sam, Noah, and Priya. Second, the smaller, orange circle, students who take advanced calculus. Notice that the entire orange circle sits inside the blue circle. This is because both Sam and Noah, the students taking advanced calculus, are also automatically part of the larger maths group. Therefore, set A, advanced calculus, is a subset of set B, maths. In logic, we write this as A is a subset of B. Everything in A is also in B, but there are some students in B, like Mia and Priya, who are not in A. It's a perfect visual for showing total containment within a category. Now, let's tackle one of the most common ways we use Venn diagrams, showing intersecting sets. This happens when 2 different categories share some of the same members. To illustrate this, let's look at the data in image_A0D1.jpg. We have our universal set, the large gray rectangle, containing all students in class 10A. Inside, we have 2 specific groups. Set A, the blue circle, students taking chemistry, Mia, Sam, and Noah. Set B, the orange circle, students taking physics, Liam, Chloe, and Ben. Notice that these 2 circles are not separate, and one is not inside the other. They overlap. This overlapping middle section is called the intersection. This is where the 2 sets share common elements. In this case, both Aisha and Priya are in the chemistry class and the physics class. Therefore, their names, and their icons, live in that shared green space. So, the intersection represents the elements that belong to both set A and set B at the same time. If a student is outside both circles, like Olivia or David, they are part of neither group. It's a perfect visual for finding common ground between two different topics. Today, we're looking at one of the simplest, yet most fundamental relationships between sets, the equal set. What is an equal set? Put simply, two sets are equal if they contain exactly the same elements. It doesn't matter how the sets are defined, or what order the elements are listed in. If the contents are identical, the sets are identical. Let's visualize this concept using the data and image. We have our universal set, U, all students in class 10A. Inside this universe, we have two defined groups. Set A, the blue inner circle, students who like algebra. This includes Mia, Sam, Noah, and Priya. Set B, the orange outer circle, students who like calculus. Notice anything? Look closely at the names inside the orange circle for calculus. It's the exact same list: Mia, Sam, Noah, and Priya. Every student who likes algebra also likes calculus, and only the students who like algebra also like calculus. Because the membership of both sets is identical, set A and set B are equal sets. When we draw this on a Venn diagram, the result is unique. We don't see two separate circles. Instead, the circle for set A is perfectly superimposed inside the circle for set B. They completely overlap to form a single identity. In mathematical terms, we write this simply as A equals B if the elements are the same, the sets are the same. Ever wonder how to group everything else? That's the complement of a set, A. As seen in this diagram, we have our universal set of students. Set A contains those who like maths. The complement, A, is simply everyone else, the students who don't like maths. They exist within the universe, but outside the boundaries of set A. It's a simple way to define a group by what it is not. So, that's how you handle different set relationships. From disjoint sets to complements, you're now ready to visualize any data set that comes your way. If this video helped you out, hit that subscribe button for more bite-sized math tutorials. See you in the next one.